In this talk, I hope to argue that today's so-called scale-out shared nothing architectures and scale-up shared memory architectures, the difference between these two are already blurring, and I'll be making a case for bridging the difference. This is joint work with Vasilis, Antonis, Arpit, Boris, and Stefan. Okay. So I don't believe that this is the audience for me to argue that cloud applications are happening and these applications produce lots of data and they're really data intensive and they need scalable infrastructures which can store data in memory, lots of data in memory, and also serve data at a high latency and throughput. So basically, there are two approaches to meet the scaling demands. One is called scale up, where essentially you add resources to a single server to form this so-called shared memory multiprocessor. The other approach is to so-called scale out, where the idea is that you loosely couple different servers within a rack to form this so-called scale out shared nothing computer. Right? Okay, let's understand these two better. What you get with scale-up is essentially this logical view of shared memory, and you can basically program with what is this load-store interface. And what it also provides you is this ability to transparently cache stuff, in other words, replication, right? And the associated consistency enforcement, which it performs through hardware-enforced cache coherence protocols. So let's look at scale-up a little bit closer. So let's say you have the data for an address X, which is there in this memory location, Pn, right, the node N, and you want the data from this node, the first node. So you basically issue a load which from the processor, and you do nothing, right? So basically the load gets into the CC NUMA logic fabric, goes through the interconnect, magically gets this data back to the interconnect, and comes back. Right? Essentially, what happens is that all of the communication associated with loading this remote data happens to this CC NUMA fabric and the interconnect transparently. Right? And of course, what happens then is that this data of X gets cached into the local cache, and so that if there's a subsequent load, you don't even need to go out, and it can be served from the cache. What it also means is that when you do perform a store, then you would need to invalidate other shared copies, in other words, to enforce consistency. And that also happens transparently, right, without software explicitly passing messages through the CC NUMA interface. Right? So that's good for giving this transparent replication. But the problem is that it's been traditionally hard to, when you say buy a shared memory multiprocessor for, say, n nodes, scaling that further, right, it would be harder. And in a similar vein, managing fault tolerance, for example, if a node fails, is traditionally hard in this setup. And the final killer is that the cost of these are, again, been very high. For example, if you buy something like SGI, let's say something like with 256 sockets, it might cost you up to, say, more than $1 million. So in contrast, what you do with a scale-out architecture is that you pool together resources of servers, right, the memory and processor resources, and you basically use middleware software such as key value stores to map and split the data set into different servers and access the data using the API provided by the middleware. For example, gets and puts. So which means that, let's say, if you have an object which you need to access from node 1, and it's mapped in node n, and it lies in this memory node, right? And which means that you need to actually retrieve data by explicitly talking to the remote node, right? And this involves kind of messages traversing through the network stack and also the CPU of both the target and the source. Right? Which means that if you have a data set with hotspots, like Boris Grott in the talk on Monday talked talked about how data sets have this natural skew in them, which means that it's likely that nodes can get congested, right, and it's susceptible to hotspots. Again, the network and the CPU of the congested nodes can limit the throughput of the system. So in order to mitigate this problem, this recent advent of RDMA, what it helps is that you can leverage this RDMA protocol to essentially distribute these remote requests across these nodes, right? Which essentially means that because of RDMA's capabilities, CPU is no longer the bottleneck. But the problem is that the network is still a bottleneck. Right? So as it has been observed in several of these papers which use RDMA-based key value store implementation, scaling the key value store past, say, 20 servers has been hard. And in order to understand this better, what we did was we modeled this using a discrete event-based simulator, which modeling the memory system, the network, and also the processors. And we considered a workload using a Zipf a power law distribution. And we found that, similar to the observed data, throughput saturates around 20 to 30 servers. And increasing the server count from, say, something like 20 to 100 only yields a very small throughput increase. Right? And the data corroborated by our kind of additional statistics where we find that the reason is actually because of the network bottleneck. And in fact, we find that there is a big variance in terms of the network utilization, varying from 50% to lightly loaded ones to 100% for ones which are the bottleneck. Now let's take a step back, right? So we started with something like a scale-out processor, right? In order to be able to program with it, as I would claim, right? So you needed to use middleware such as key value stores, and I would argue that in some sense it is like providing a global address space, right? Where the keys are essentially the global address. And then what you did was use something like NUMA to distribute requests, right? So using RDMA, capabilities like RDMA. So what is essentially missing is this ability of transparent caching and consistency protocols that are provided by today's scale-up systems. So the question is, can we just bridge this? So in fact, because of this skewed nature of data sets, it is actually a good case for performing something like performing caching. Because as we can look at this graph, even with a very small percentage of cache, it's like 0.1% of the overall data set, you can get a very good hit rate, right? And that's essentially because of the skewed data sets, right, which follow power law distributions. But again, a single cache, if you want to use a single cache in your system, that itself can become a bottleneck. So then the question is, why not replicate this cache in every node of the rack, right? So in essence, something like this. Right? You have this scale-out system, and in these red parts of memory is reserved as a cache, and there you cache all the hot, skewed data items. That's essentially the simple idea here. So then the problem here is, what about consistency? Obviously, things would work fine if there is only read-only data, but writes do happen in these workloads, right? So essentially, all the writes to the hot data would need to be propagated and made visible to all other caches or replicas here, right? So the question here is that, would the cost of propagating these writes, right, exceed the benefit provided by caching? That's essentially the question here. In some sense, intuitively, that one would think is a function of the write ratio. And luckily, these data sets traditionally have very small write ratios. Like Facebook, for example, reports something like 0.8% of writes. But the challenge here is that the write propagation, the protocol which is in charge of propagating the writes, must itself be free of hotspots, because in the scalable system, that could easily become the bottleneck. And another challenge here is that in this domain, there are a plethora of consistency models, right? Ranging from kind of eventual consistency to strict transactional serializability. So that is yet another challenge here. In some sense, we would need to have programmable protocols for various different consistency models. So those are the challenges here. So what we started was look at two of the consistency models, right? In particular, we first looked at eventual consistency. Again, eventual consistency has various definitions in the literature. And what we used was a particularly strong interpretation of eventual consistency, which is write serialization, right? So if you're an architecture person, think of it as per key sequential consistency, or per key, which is similar to the requirements of coherence in shared memory multiprocessors. So with per key sequential consistency, informally, what we want is for everybody to agree on the order of the writes, right? Let's say you have 4 processes here, right, or sessions, if you may, right? And let's say that the first process here puts to the key a value of 1, and the fourth one puts a value of 2. Then you don't want, if you had 2 consecutive gets, you don't want P2 to read 1, 2, and P3 to read 2, 1, right? So you don't want the situation. Okay, so how would you enforce eventual consistency? So the straightforward way to think about this is to follow the philosophy of protocols similar to shared memory protocols, right? And one way shared memory multiprocessors do these protocols is to use serialization points. On a write, essentially, you go to the home node, or called a directory in the shared memory world, or the primary, right, to serialize, right? And the home or the directory broadcasts the value to all the replicas or the cache copies. But the problem here is that, as we discussed earlier, this serialization point could be a bottleneck in this kind of throughput limited system. So what could we do? So again, we can borrow an idea which dates back to 2000, right, called timestamp stooping, or again in the DSM world, using Lamport timestamps to have distributed protocols for ensuring serializability. Right? So the idea is simple. Everybody maintains local logical Lamport timestamps, right? On a write, you increment the timestamp and broadcast the timestamp along with the data. On somebody receiving an update, you would ignore the timestamp of the update if the timestamp is lesser than your local timestamp. In doing so, you kind of maintain the invariant that the last writer, right, logically, last writer wins. Of course, you need to break ties using something like the processor ID. Right? So this is great, but how about something if you go stronger? Let's say if you want something like per key linearizability. What does linearizability mean? Linearizability informally, first of all, requires that everybody should agree on the order of writes, like serializability, but also that a write must not return success, right, until it has been propagated to all replicas. In essence, you want to avoid this situation. Let's say this is real time, right, and you have, again, 2 processes or sessions, whatever you like, and you do a put to this key, and you write a value of 1, okay? And then in real time, later, after it has been reported as success, this should not report a value of 0. Note that something like sequential consistency, per key sequential consistency, this is perfectly fine. Because in logical time, you are free to reorder this before, and nothing is affected. But as far as linearizability is concerned, this needs to be prevented, right? So think of this situation as something like you're using Amazon and you put an item in your web cart, right? And later use another session and find that it's not there. You don't want this situation. So that's why linearizability is important. Okay? So how do you enforce this kind of stronger linearizability constraint? Intuitively, you need a 2-phase protocol here. And this is due to work by Garui in 2007. so what you do is, on a write, in the phase 1, you broadcast invalidates with Lamport timestamps, okay? But you collect all acknowledgements. Only then you propagate the updates. Okay? In doing so, you maintain the invariant that no, you're not reporting a success until the write has been propagated to all caches or replicas. But the challenge here is that, as alluded by David in his talk yesterday, that this simple protocol is only the partial story, right? You need to handle all the ugly transient states, or the big table, as he called it, right? So, for example, what to do when there is a write to a key that's waiting for acknowledgements? Would you go ahead with the write, right? So these are tricky corner cases. So what we did was consider 2 variants of this protocol, right? And those 2 variants in the architecture world are called stalling and non-stalling variants, right? And we specified those 2 variants and completely and model check them for safety, right? Which is guaranteeing the consistency model. I'm not going to go into these protocols, but I'll just skip and very briefly go into a real implementation, right? So when we use these ideas to build a key value store, LAC level key value store, we had to go into a number of RDMA related issues. Things like what RDMA verbs need to be used. Should we use one-sided ones or two-sided ones, for example? And agreeing with Herd, we found that actually two-sided using datagram sense actually is work better in this situation. And we also found that minimizing connections was very important, because we needed this all-to-all communication within the rack, right? And so minimizing the connections was very important, and we proposed a bunch of techniques to do that. Also, concurrency issues, in other words, write single copy atomicity in ARM's parlance, or this write atomicity, is also an important issue, even without replication, right? And there's a tension between load balance and the synchronization overhead involved in guaranteeing this write atomicity. And I'm not going to those things here, but the idea here is that because we were able to filter the skew using the caches, we could actually avoid synchronization overhead in the data store. Okay, so some numbers from simulations, right? So this is using the same simulation infrastructure that we talked about. So basically, these are 1% writes. And the blue bar here is the baseline using RDMA, something like farm, right? Using RDMA, but without caching. And we see that for the gray bar here shows the throughput we achieved, guaranteeing serializability, per key serializability, or eventual consistency. And we are able to get 4x the throughput of the baseline. And even for something like strong consistency, we are able to get 3x the throughput. And this is for 1% writes, which is slightly higher than the amount of writes reported by Facebook. And of course, if you increase the writes, then you would need more bandwidth. And so proportionally, the throughput we get decreases. But we're still able to get 3x the throughput for eventual consistency. And this is just a limit study to say how much are we sensitive to write ratios. And intuitively, there is going to be a write ratio where we break even, right? And the baseline will be better. And that we find that is around 9%, right? This curve, orange curve here, is for strong consistency, and the red curve shows for eventual consistency. And that is 24% for eventual consistency. So up to 24% writes we can tolerate, right, with caching. Okay, so this is some preliminary numbers in our real implementation. Treat this with caution. These are very preliminary. But what we did was use InfiniBand NICs and InfiniBand switch real implementation with just 5 servers to start, right? And one thing we observed was because of the low server count, the baseline with skew and baseline with uniform are actually quite similar to each other, the throughput. But yet we see that caching actually improves even over uniform. And the idea here is similar to shared memory multiprocessor. We take advantage of skew. Right? Skew is not a kind of an enemy for us. We take advantage of it. So again, just to summarize, scale-out architectures and scale-up architectures, I would argue, are converging, because you're already having this middleware such as key value stores, which provide this shared namespace. And then you have techniques which are like quasi-NUMA, right? Things like RDMA, where you offload request processing. And what is left is really caching. And I would argue that there's a strong case to do caching because of the zip distribution again, parallel distributions. There is a huge win there, potentially. And that's what we have argued for. Symmetric caching keeps it simple, captures all skewed data, and we have proposed distributed consistency protocols without a serialization point. And that is mainly the challenge that we had to overcome here. And looking ahead, we are planning to look at more consistency models, which is, we have looked at per key consistency models we want to do across key ordering, right? And of course, this question of how to scale to multiple racks. So again, the problem there is that eventually we would not scale, right, when you increase the number of racks. And at some point, we would have to use some kind of scoped consistency models. Again, in the heterogeneous computing world, these are in use currently, right? In GPU, CPU world, for example, where you assign scopes to different keys, so to speak. And of course, we have not considered failures or availability. And yet another opportunity here is that if you had something like byte addressable persistent memory, right, could you also guarantee durability using similar protocols in spirit to consistency protocols? That's an intriguing question that we are thinking about. So in some sense, what is exciting is that if you have a rack scale system with persistent memory, and if you allowed caching, right, guaranteeing consistency, availability through replication, and durability is essentially about protocols for propagating values to replicas. And that we know, we have spent a lot of time in the computer architecture world to look at these things. And to look at these problems in this context seems like an exciting intersection between these two fields.